Hello, 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 hello. Hi. So my name is Dilshad and I'm here to discuss IICPC's Codefest 2026 Prelims contest. Okay. So has this mirror contest that has been previously said. So I'll just start discussing the problems now. Okay. So let's start with the first problem. This is the A problem. So let's read this problem. So we are given an. So let's suppose there is an array A and we are calculating a certain matrix B. Okay, and this matrix is being calculated in like this. So the I comma jth entry is equals to AI plus AJ. Okay, and now we no longer know about the array A, and we want to want to know what's the array A, and we are given the matrix B. Okay, so basically, we are given this matrix B, which was constructed in this way, and we have to go back, like we have to just trace back to our original array A, and the constraints are like very small. Okay, so here's this problem A. So like B of I comma jth entry is what? It is just AI plus AJ, right? So you would notice that for I equals to J, my B of I comma I is equals to what? 2 of AI, right? So from here, I can directly go back to whatever my element is. So if I want to know what A of 1 is, it is basically B of 1 comma 1 by 2, right? Similarly for B2, sorry, similarly for A2, it is simply B of 2 comma 2 by 2, right? And in this way, we are able to trace back to our original array A, right? So this is my final solution, and the let's look into the code for once. So here's the code, right? So I have just taken the matrix as input, and then I'm just outputting uh, my array, right? So yeah, that's that. So the overall time complexity of this approach is big of n square because we are taking matrix as an input, right? Otherwise, you can say that our solution is just of big of n. If yeah. And space complexity is again big O of n square, and like we can say that it is big O of n as well if we assume that this matrix is being passed as a reference in some function, but it is not, so it is big O of n square only. So let's move to the next question. This is the second question, so let's read this question. Alice and Bob are playing a game on an array of size n, and it is guaranteed that either AI is equals to 1 or AI is equals to minus 1, right? In a single move, a player is allowed to do this following thing. So it chooses a subarray of A, and the product of this subarray has to be minus 1, and then we can delete this subarray. Okay, and concatenating the rest of the two subarrays. Okay, and the order remains the same. So we have to tell like who wins the game. Okay, and if Alice wins the game, then we have to tell the first move of Alice, what Alice is going to do, right? So, like important observation here is the subarray which we are choosing, the product has to be negative. It has to be minus one. Okay, so uh, and the player who is not able to make a move is going to lose, right? Yeah. So the player who is not able to move, who is not able to make the move is going to lose, right? So if Alice wants to win, if Alice wants to win, the game should last for odd number of times, right? So the game would last for let's say two of m plus one rounds. because then only Alice would be making the last move and then Bob would lose. Okay, so this number over here is odd, right? And for every operation, the subarray we are choosing has the product being negative. Okay, so the subarray must also contain odd number of minus ones, because then only the product of the subarray is going to be negative, right? So, uh, so in every round we are choosing odd number of minus ones, right? So from this we can say that for Alice to win, one necessary condition is the array must contain odd number of minus ones, right? Odd number of minus ones. Or we can say that the product of this original array has to be negative. This is a necessary condition. And this is also a sufficient condition. Why? Because we can always choose our first move as the whole array. So if we are going to choose if we are going to choose the whole array as our first move, then like the array is empty after in the second move. Okay, so then Bob loses and Alice wins. So yeah, so this is the necessary and sufficient condition for Alice to win, and one way to win is just output the subarray 1 comma n. Okay, so let's look into the code. So I'm just taking my array as input, and then I'm just counting number of minus ones. If it is odd, then Alice is going to win, and the first move can just be the whole array, and if it is even, then Bob wins. So the overall time complexity is just big O of n, and space complexity is also just big O of n. Let's move on to the next question. Yeah. So we are given this array A, and we have to perform two types of operation. So select an integer x, and we can update uh, for every I from 1 to n, we can update it as absolute of ai minus x. Okay, and this move has cost 0. And the second type of move is like we can make ai is equals to ai mod x, and this has the cost 1. And you must notice that x is between 2 to n. Okay, so x should be less than or equals to n, and x cannot be 1. And we have to find the minimum total cost to convert a into all zeros, right? And we also need to find a sequence of operations of at most 15. Okay, so we don't have to minimize the number of operations, but we have to minimize the total cost. And yeah, and n is like 1000. Okay, but still we can't apply n square because there are 100 test cases, right? So first observation is this question is actually similar to a previous code forces contest problem. So in that we were given the same thing, but there was only type 1 operation. Okay, type 1 operation, like we were allowed to do ai minus x, choose x, and for every I, for all I, like make ai equals to this. Okay, but in that but in that we were just asked that when it is not possible to make this whole array equal to array of all zeros, just okay. Yeah, we were asked just that. And if it is possible to make the whole array as just the array of zeros, then we had to tell a sequence of at most 40 operations. Like in that also we didn't have to like minimize the number of operations, right? So so when it is not possible, so it is not possible when the whole array contains when the array contains elements of different parity. Why? So whatever x you are choosing, let's say x is even, right? And let's say AI contains what? Let's say there exists two indices I and j, AI is even and AJ is odd. Okay. So if we are choosing X as even, then after this operation, AI remains as even and AJ also remains as odd, right? So the parity is being what? The parity remains same when X is even. Okay. And if we are choosing X as odd, X is odd, then AI from even to, so like previously it was even, but now it is going to be what? It is going to be odd. And AJ, which was previously odd, but since we are subtracting an odd number from it, so then it gets transformed to what? It gets transformed to an even number. So what I am saying from this fact is, no matter whatever value you chooses for any operation of type 1, you cannot like reduce all the numbers to just one parity. Okay, so like if there exist two numbers with different parity, then there would always exist like numbers of different parity. Okay, so no matter how you apply the operation, there is going to remain some number of even numbers and some number of odd numbers, and the smallest even number that you can reduce it to is just zeros, and the smallest odd number that you can reduce it to is just ones, right? So from there you can't reduce with type 1 operation, right? And what is a possible way to reduce any array into just arrays of zeros and ones? So one possible way is to do what? Like just choose x is equals to mx by 2, right? I should write something like this. I should write, yeah. So if you choose x is equals to ceil of maximum by 2, then what is going to happen is, so let's say my array was something like this, mx and then this. Okay. So the range of the elements is like 1 to mx. Okay. But when you are going to choose x is equals to half of the maximum value, then the range is reduced to half. So the range is just reduced to what? Range is reduced to mx minus this thing. Yeah, so the range is going to be like similar to mx by 2. Okay. So in every operation, you can reduce the range to half. So this way you can choose your x for 10 or 11 operations, and then your whole array is going to reduce to what? Like just zeros or and ones. Okay. Right? Yeah, right. So let's say you have reduced. So what is going to happen? Either my whole array has been converted to zeros, or or uh, or the array contains some zeros and some ones. And till now, our cost is zero because we have only used operations of type 1 only. So, but then you can't reduce this array into just arrays of whole zeros with type 1 operation. So you would have to use type 2 operation. So how we are going to use the type 2 operation? So one way to do is what you can do is, so if you would so yeah so what was the actual actual barrier to our solution? So the actual barrier was just we were not able to transform the two parities into one single parity. Okay. So we have to choose, we have to do some sequence of operation from which we can change this whole array into just elements with the same parity. Okay, we have to transform into that. So how we are going to do that? So clearly, like whatever x you are going to choose, so for type 2 operation, x has to be greater than or equals to 2, right? So if you would choose a type 2 operation on this array, then nothing would happen, right? So we would have to choose some type 1 operation to transform it into something else. So whatever type 1 operation you are going to choose, Like let's say I choose Y. Okay. So then the whole array gets converted to what? Like Y and Y minus 1, right? And what we want to do is we want to do some kind of type 2 operation such that this array gets converted to an array which has the same parity. What if the x I am choosing is exactly equals to y? So if I would choose exactly equals to y, then this array gets converted to what? It gets converted to zeros, and this gets converted to y minus 1, right? So we want to make 0, like the parity of 0 is what? Like it is 0. And the parity of y minus 1, that has to be made equal to the parity of 0. Then only we will be able to find some sequence of operations with just type 1, so that my array gets reduced to all zeros. So y minus 1 should be congruent to 0, right? So y should be congruent to 1, right? So when I was using this operation, I would have to choose some number y, like some odd number y, okay? But obviously we can't choose y is equals to 1, because after that my array will remain same, like zeros and ones both will be there. So if I would choose y is equals to 3, then this array gets transformed to what? Like threes and twos, and then I would apply a type 2 operation with x is equals to 3, and then my array gets transformed to what? Like zeros and then twos, and then you can apply two type 1 operation of x with x is equals to 1 and x is equals to 1, and then the array will be reduced to what? Zeros only. Okay, so this is what I have done in my solution. Let's look into the code. So yeah, you can see, so I have just taken the input, and then I'm maintaining this vector of operations. Okay, I'm just checking if the largest element, like while the largest element is greater than 1, then I'm doing this operation. Doing what? Like I'm choosing the x as the largest element, plus the seal of largest element by 2. Okay, seal of that. And then I'm transforming the array, and then I'm sorting the whole array, right? And if the last element is equals to what? 1. Sorry, if the first element is equals to 1, that means that the whole array has been converted to what? Has been converted to all ones. Then yeah, so if it has been converted to all ones, right, then I don't have to do anything. I don't have to use type 1 operation. So in that case, my answer is just going to be 0, right? Otherwise, like my minimum cost is going to be 1, and this is the same sequence of operations that I have earlier talked about. Okay, and then I'm just printing my answer, right? So the overall time complexity of this approach is big of n log n, and space complexity is big of n. Yeah, it is not big of n log n, it is big of log a. So a is what? A is just the uh, like maximum AI. Okay, AMX, whatever. Okay, so let's move on to the next question. So let's read this question. So this question is similar to our second question. Alice and Bob are playing again on the same array of ones and minus ones. The difference is just that in the previous one we were supposed to choose a subarray uh, with a negative uh, with a negative product, but in this one we have to choose a subarray with a positive product. Okay, and then delete this subarray and then concatenate the rest, and then we are just asked who wins. If both the player plays optimally, then who wins, Alice or Bob? and the constraints are like the normal constraints, okay, 2e5. So, so the like my question has been changed in a way that I have to use even number of zeros in this. So I have to choose even number of minus ones in this array, right? So in every operation we are choosing even number of minus one. So if there is like odd number of minus ones, then it is not possible, right? So if there is odd number of minus one, then it is not possible for Alice to win. Okay. And if it is, and in the question we have been asked that if Alice is going to win, then we have to tell the first operation that Alice is going to choose. Okay. Yeah, right. So this is actually a little harder than the previous one. So, uh, so if you're not able to think anything, then the best way to approach this is like try to solve for simpler cases, then only proceed to like more complex ones. Okay. So let's talk about yeah. No, like I said that if there exists odd number of minus ones, then Alice is going to lose. Like that is not correct. Alice can force a win in that as well. And if there exists an even number of minus ones, then Alice can just print the whole array, and then Alice can win. Okay, print the whole array she can apply the operation on the whole array 1 to n, and then she wins. Okay, so that is trivial. So from here on, we are assuming that the array contains odd number of minus ones. Okay, odd number of minus ones, right? So like the smallest odd number is what? It is one. So let's try to think for when the array contains only one minus one. Okay, yeah, and like for further discussion, I am going to use I'll just call minus one as one, and I'll call 1 as 0. Okay. So in that sense, it will be easier to discuss. So then again, like the thing remains same. I have to choose even number of ones. Okay. That's all. So there contains some number of zeros, then there is one, then again there contains some number of zeros. Okay. Like I am just talking about a simpler case when the number of ones is just equals to one. Okay. I'm talking about this case. So, first of all, uh, let's denote the number of zeros in the left side as x and the number of zeros in the right side as y, right? So, if both x and y is equals to 0, then Alice can't do anything. So, Alice loses, Bob wins. Okay, Bob wins. Let's say x is equals to 0 and y not equals to 0. Like one of them is 0 and the other one is not 0. So, the array looks like something like this 1, 0, 0. Okay, some number of zeros. So in this way, Alice is just going to do what? Like it can reduce all the zeros. Like it can just delete all the zeros in just one operation. So in this case, Alice wins. Okay. So when x is equals to 0 and y is greater than 0, Alice wins. Similarly, for y equals to 0 and x is greater than 0, again Alice wins, right? So let's talk about when both x and y are greater than 0. Okay, so x is also greater than 0 and y is also greater than 0. So then what is going to happen? So the smallest pair of number, where x and y both are greater than 0, like we can assume it at as x is equals to 1 and y is equals to 1. Okay, so this basically means that there is a 1 and there is a 0 on either side. So who is going to win for this array? So this one example was given in the sample test cases as well. So in this case, Bob is going to win. Why? Because Alice, like no one can include this one in any operation. No one can include this one, right? Because we have to choose even number of ones, and there's only one, so we can't choose this one. So either we are going to apply the operation on the left side only or the right side only, and wherever we are going to apply, this will get reduced to either one of these two cases, and from that, the player who is going to make the turn is going to win. So in this, for this particular array, Bob wins. Okay. So what are the cases when Bob is winning? When x is equals to y equals to 0, Bob wins. When x is equals to y is equals to 1, again Bob wins. Okay. So we'll just keep track when Bob is going to win. Okay. So then you will see the pattern. So let's talk about when x is equals to 1 and y is greater than 1. Then what is going to happen? So here's a 0 and here's a 1, and here are some number of zeros. Okay. Since we know that x is equals to 1 and y is equals to 1 is a losing state, I can force the other player to go into a losing state. Like I can choose some number of y. So let's say there are y greater than one number of zeros here. So I can always choose y number of zeros in the right side, and I can just delete them, and then it will go back to what? It will go back to a losing state. So then Alice is going to win, right? So for x is equals to 1 and y greater than 1, again Alice wins, and vice versa. Okay, for y is equals to 0 and x greater than 1, again Alice wins. Okay, so let's talk about when x is equals to 2 and y is equals to 2. Again, the same argument that we can't include 1 in our operation. So we are going to apply the operation on one side of the array as well. So one side of the uh, array only. So let's say we are applying on the right side. So x equals to 2 remains same. So y is either going to get converted to 0 or 1. So then it goes back to what? Then it goes back to a winning state. Hence, this state again is losing state. So you can see that x is equals to y is equals to 2 is also a losing state. That means that Bob is going to win. Okay. So doing this argument for every number, we can conclude that for every state with x is equals to y, Alice is going to lose. Alice loses. And for all the other cases, otherwise Alice wins. Otherwise Alice wins. Okay. But this is we have arrived for a simpler case, that is there is only one in this whole array, right? There's only one in this whole array. So let's say there contains greater than one. So there would contain at least three ones, because there are odd number of ones in this array, right? Uh, right, that we have assumed in the beginning. So let's say that it contains three number of ones. Can we always reduce this array into a winning state? Sorry, a losing state. We can. Okay. What is a losing state? When x is equals to y, right? So we will count the number of zeros in the left hand side and we'll count the number of zeros in the right side of the rightmost one, like number of zeros in the left side of the leftmost one and the number of zeros in the right side of the rightmost one. Whatever this x and y is, so whatever this x and y is, what we can do is, so let's say x is equals to y. Initially x is equals to y. Then what we can do is, we can choose to keep 1 1 over here, and then I can reduce the all the like the whole remaining array. Then we go back to a losing state. Let's say x is greater than y. Then what I'm going to do is I'm going to keep this one in the array, and then I'm going to reduce this remaining array as it is, and then I'll also remove some number of zeros so that x becomes equals to y. Similarly, when x is less than y, I'm going to remove some number of zeros from here, and then I'll keep this one in the array as it is. Okay, so let's look at the code for this. So, so I am just taking the array as input, and then I am checking like what the product is. So if it is even, Alice is just going to win in one single move. Otherwise, what I'm doing is I'm just counting like how many minus ones are there. Okay, so if there exists only one minus one, then only Alice may lose. Otherwise, Alice is always going to win. So I am counting how many number of ones are there in the left and how many number of ones are there in the right, right? And if it is the case of there is only one in the whole array, sorry, minus one in the whole array, then I just have to check if the left number of zeros equals to right, then only Alice is going to lose. Otherwise, Alice is going to win. Okay, and again, Alice is going to win. Okay, and this L and R denotes what subarray I am going to delete. Okay, so I am choosing the subarray in the same way that I have described over here. Okay, so the overall complexity is big O of n, and space complexity is also big O of n. Right. So let's move on to the next question. So let's read this problem. We are given an integer n. We call a matrix W of size n cross n good if it satisfies some certain conditions. That the matrix is symmetric and the diagonal elements are zero, and this set forms a permutation of the integers. Okay, so basically the upper right corner of this matrix contains a permutation of from 1 to n into n minus 1 by 2. Okay, so there are n into n minus 1 by 2 entries in the upper right corner. So it should contain what? It should contain a permutation of 1 to that number. Okay, and for this matrix, for a good matrix, we define f of w in this following way. So consider a complete weighted undirected graph of n vertices with weight between the weight of the of any edge between I and j is just wij. Okay, so this matrix just denotes what is my weight of the edges between ith node and the jth node. And then f of w is defined as the weight of the minimum spanning tree, right? We are given two integers n and k, and we just have to say that does there exist a matrix w such that f of w is exactly equals to k, and we have to print such a matrix if it exists. And the constraints are n being from just 1 to 50. Okay, So this whole matrix denotes what? Like I comma jth, it denotes what? It denotes the weight between the ith node and the jth node. Okay, it is a complete graph. Like from every node there exists an edge to all other nodes. Okay, and from this node as well there exists an edge from this, and from this node as well there exists an edge, and like that. Okay, so this is basically complete graph. Yeah, like that. Okay, so from this complete graph we are taking an MST. Okay, we just have to tell, does there exist an MST uh, with the sum of the weights being exactly equals to k. Okay, smallest value of k. Like I can always make the MST with the edges 1 up until what? N minus 1. S- Right. So k has to be greater than or equals to n minus 1 into n upon 2. Right. And what is the maximum that k can be? So if I can find what is my maximum, then the question is almost solved. But right. So let's look into this matrix for once. So this entry denotes what? So this entry denotes the edge between the first node and the second node. So this is my first node, this is my second node. Okay. So I am going to start constructing my graph from my first node only. Okay. Like to keep things simpler. Also, like it doesn't depend how you label the nodes. Okay. So the overall structure should be like how do I say it? Invariant to whatever label you are giving to the node. Okay, so and also you must have studied that if I just like from any graph, if I just start choosing edges with the minimum weight, and also that edge uh, should not contribute to a cycle, like whatever the existing graph that I have made, if adding that edge doesn't make any cycle, then I can add that edge. Okay, so among all those edges, I just choose the smallest edge that is possible. Okay, smallest weight of the edge that is possible. So it is pretty clear that in any MST that I am going to have, edge weight with 1 is always going to be there, right? So 1 is always going to be there. So from node 1 and 2, let's say I have made an edge with weight 1. Now comes my third node. Now comes my third node. Okay. So, uh, like third node, by adding the third node, I can have two edges. Like I can have one edge from 1 and I can have the second edge from 2, right? So it is pretty clear that the edge width with 2 should also be there. So uh, let's say this is my third node and this edge has the weight 2. Okay. This edge had the weight 2, right? But you can also have one edge over here, and whatever weight you are going to give, let's say whatever x that I am going to give, then what is going to happen is in whatever MST that I'm going to have, this x is not. is never going to be in an MST if I like if I give this edge as the weight 1 and if I give this edge as the weight 2, then if then whatever value I choose, let's say I choose the smallest possible value, that is 3. So even if I give this edge as the weight 3, it can never be included in an MST, right? So basically I have been able to make a breathing room for the edges that I don't want to have in the MST. I can put them over here. So what if I add my fourth node? Let's say this is the fourth node. So from this fourth node, there again can be what? There again can be three edges, and one of the and from these three edges, the edge with the smallest width is always going to be there. Okay. So let's say I have not included three in this. So I'll have to include four in this. Going to be is going to be in the minimum spanning tree. But now I have two edges in which I can keep any edge weight, and that edge weight is not going to be considered in the MST, right? So I can keep 5 and 6 or whatever. I can also keep here, let's say 100. Okay, if 100 is in within the bounds. So even if I keep 100 over here, this edge is not going to get considered, and this 5 also here is not going to be ever get considered in the MST, right? So what I have been able to tell from here is that only uh, these edge weights matter. Okay, so I'll have to keep one over here, I'll have to keep two over here, but then I have made a breathing room for three. Okay, and I'll have to keep either three or four. So if I am keeping three over here, then I can go to four. Otherwise, I can keep three here as well. Okay, and then again I have made some breathing rooms, right? So let's say we are at the let's say this is one, this is two. Let's say we are at the ith one. Okay. So what are the possible edge weights that I can have in here? So among all these edges, so what is the maximum edge weight that it can have over here? So to have the maximum edge weight, so to have something over here, we have to keep all the edge weights inside this rectangle, in this subrectangle, okay, in this triangle, okay. So whatever edge weight that I am going to have over here, all the edge weights that are less than this, I have to somehow place them in this subrectangle. So what is the maximum number of numbers that I can place in this in this triangle? So the maximum number of um, so the maximum number of numbers that I can place in this triangle is what? Is just this. So in the first row, there is just one number. In the second row, there is two number, and so on. And in the ith row, so before the ith row, there is I num minus one numbers. So the total number of numbers is what? I minus one into I by two, and just the next number, I can keep it at this position, right? So this is the maximum number that I can have ith uh, in the ith column. Again, I'm counting from the second row, okay? I'm not counting from the first row. Like the first element is just going to be zero. I'm not counting from there. I'm counting from the position of one, okay? So the ith position can have a maximum of this, right? And it can have any number before that. Okay, so what is our question? Our question is I have to choose some sequence of numbers from I have to choose some sequence of numbers of size n minus 1 such that their whole sum is exactly equals to k. Okay, so here's my solution. So what I can do is I can start with an initial choice. My initial choice can be what? Simply just 1, 2, 3, 4. up until n minus 1, right? And let's say this sum is still less than k, okay? Then what I can do is I can increase this n minus 1 to n. Then this sum gets initially my sum was this, and then it gets incremented by 1. So I can increase n minus 1 to n. Then I can again increment it to like I can keep incrementing it. I the until what? Until either I can't increment it, right? It has some maximum value. The maximum value is just this. I'll put I is equals to n minus 1. Then whatever value I'm getting, that is the maximum value that I can increment it to. Like you can also verify for I is equals to 1, this is 1. For I is equals to 2, this is 2, which is also true from which I can also see from the matrix itself, right? So in this way, I can just keep incrementing until either two things happen, or or what, or I have reached the maximum value of for this n minus 1th edge. Okay, so if I have reached this maximum value for this ns minus 1 edge, then I can keep incrementing my n minus 2th edge, and I do this thing, like I keep doing this thing. Okay, then in the end I am going to have some sequence of n minus 1 numbers whose sum is going to be equals to k. Okay, assuming assuming that it is even possible. So when it is not possible, so it is not possible if k is greater than some certain number. So what is that certain number? So that certain number is just this. So what is the maximum k that I can reach? So let's say this is 1, then this is 2. I keep 3 over here, 4, 5, 6, 7, 8, 9, 10. Yeah, right. So if I construct my matrix like this, then whatever this sum over here is, this is the maximum sum that is achievable. Okay, so if k exceeds that sum, then this k is not possible. Otherwise, it is possible. Okay, so let's look into the code to get a more clear idea. See, I'm constructing this matrix, and if k is initially less than this sum, then it is not possible. Otherwise, I'm taking this sequence of n minus 1 numbers. Okay, initially this sequence is just from 1 to n minus 1, right? And then I'm decreasing it from k as well, like to keep track of how much we require. And then I'm traversing in reverse, and then I'm checking what is the maximum number of times that I have to increment this particular number. Okay, that is basically minimum of either how much I need, that is just k, or it is the maximum possible, like the maximum possible I can increment it to, which is this number, and what this number initially is. Okay, then I'm subtracting it from k, and then I am making this as my sequence. Okay, so if if k is greater than 0, that basically indicates that we still require something. Okay, so in that case, so that indicates that k is greater than to that maximum achievable sum. Okay, then I am constructing the whole array. Like you can look into this code. I'm just constructing the matrix in this. Yeah, so the overall complexity is big O of n square, and space complexity is also big O of n square. Okay, yeah, that's that. So let's move on to the next question. For an array A, define f of A as pi of ai plus 1, and we are given two integers n and m, and we have to find the sum of f of a over all m ki power n arrays. Okay, ai is between 1 to m, right? Yeah, and fa is just this, and we have to find like they have defined some function over an array which is just this pi of adjacent numbers ka sum, and we are just taking their product. Okay, so for all possible m ki power n arrays, we have to find the sum of fa. Okay, and print its model or something. You can notice that n is less than 2e5. Okay, so this is a really good question. So you would notice that f of a is what? F of a is pi of a of I plus a of I plus 1, right? And there is no certain a given to array a, right? From I is equals to 1 to n minus 1. So uh, let's say I'm defining some other function. Okay, so the other function is what? F of n. It denotes what? It denotes that sum over all possible array A, and whatever this value is, I'm just taking the sum over all possible arrays A, right? Of arrays of size of length n and minus 1. Or even better, let's not talk about the sum, let's talk about the expectation. Okay, so expectation of this thing. Okay, so f of n basically denotes what? F of n denotes expectation of this quantity with array of size n. So that is just my f of n. Okay, so that's just the expectation. So to arrive at a solution, to arrive at a solution, we have to like come to some kind of recursion. Like we have to arrive to at some kind of recursion. From there only we would be able to do something. And from the constraints as well, you can see that like n is less than 2e5. So this indicates that there exists some big O of n solution or big O of n log n solution. Okay, right. And the most naive way to think is like there must exist some kind of DP approach for this. Okay, so if I define it like this, can I can I write f of n in terms of f of n minus 1 or some other terms? So f of n is what? F of n is basically expectation of a of n plus a of 2, a of n minus 1 plus a of n, right? So if I leave this term out, then what is this? It is basically pi of a of 1, a of 1 plus a of 2, a of n minus 2 plus a of n minus 1, and this is a of n minus 1 plus a of n, right? Right? So you would notice that this thing over here looks similar to what? F of n minus 1. Okay, f of n minus 1 into a of n minus 1 plus a of n, right? So can we just say that f of n is equals to f of n minus 1 into a of n minus 1 plus n? Like it is not that simple. Why? Because when you would like I have defined f of n as what? I have defined it as some kind of expectation, right? And when you would apply expectation over this quantity, then you can't distribute expectation over these two terms. These two terms are in multiplication. Okay, so you can't just write e of x into y equals to e of x into e of y. So for this to be true, x and y has to be independent. Okay, x and y has to be independent. Right. So are these terms independent, like f of an minus 1 and an minus 1 plus an independent? We can't say it is independent. Why? Because because uh, this term over here contains a of n minus 1. Okay, and this and there is this a of n minus 1 as well. Okay, so a of n minus 1 is there in this as well. So like these two terms are not independent. So let's say I expand this even further. Okay, so a of fn minus 1 into n minus 1 plus an into f of n minus 1. These two terms are independent. This is an, and which does not depend on f of n minus 1. Also f of n minus 1 does not depend on an. Okay, so these two terms are independent. We can distribute expectation over these two terms. What about these two? Again, these two terms are not dependent. Okay, so what I am going to do is I am going to define some other function p, So I'll define p of n as like this: a of n minus 1 plus a of n. This is the same thing as f of n, just the difference is I'm multiplying an a of n in the end. Okay, so this is my second function p of n. Okay, if I'm able to write a recursion for p of n as well, right, then I would be able to write f of n. I don't have to worry because f of n would be just what? F of n is just going to be p of n minus 1 plus a of n into f of n minus 1. And then when I would apply expectation, so I can apply expectation over this term. I can apply expectation here, and I can also apply expectation over here. Expectation of a of n is what? Like expectation of a of I, any I is just what? It is just the average, which is just m plus 1 upon 2, right? So this thing is fine. This thing is also fine. But how are we going to calculate p of n minus 1? So let's try to write some kind of recursion for p of n as well. So p of n is what? P of n is just an plus an, a1 plus a up until a of n minus 1 plus a of n, right? So let's try to expand these two terms. Okay. So a of n plus a of 2. This going until what? This going until a of n minus 2 plus a of n minus 1 into a of n minus 1 into a of n plus this same thing a of n plus a into a of n square. Okay. Now you would notice that this whole term doesn't contain a of n, and there is a of n, so like these two terms are independent. Okay, so this is not a case of worrying. We can just write this as a of f of n minus 1. This is fine. This is also fine. Like this, these two terms are independent. Okay, so this is fine. What about this? So you would notice that this thing over here is written as p of n minus 1. And again, a of n is independent of p of n minus 1. So I can write it as p of n is equals to a of n into p of n minus 1 plus a of n square into f of n minus 1. So this is the recursion for p of n. And what was my recursion for f of n? So for f of n, my recursion was just this: p of n minus 1 plus a of n into f of n minus 1. Yeah. So Yeah, and then I can just apply expectation over this whole quantities. So you can apply expectation like it is not going to make much of a difference over, like you can write it like this, and then you can apply expectation over, like expectation of a of n is just going to be m plus 1 upon 2. Again, this term over here is just m plus 1 upon 2. This is we are going to calculate, and expectation of a of n square is what? It is basically summation of I square upon m, I going from 1 to m, which is basically m into n plus 1, 2m plus 1 upon 6 into m. So this m and m cancels out. So this is basically m plus 1 into 2m plus 1 upon 6. Right. Yeah. So in this way, I can recursively calculate f of n and p of n. And what is going to be my final answer? So I have defined f of n as what? Expectation. Okay. So like this is the expectation of everything. And I was asked what? I was asked sum over all, like sum over all possible arrays. So sum is just going to be what? Expectation, whatever I have got, e of f of a, and then like I just multiply it with what? Total number of arrays. So what is my total number of arrays? So total number of arrays is just m ki power n. So I'll just multiply like f of n into m ki power n is just my final answer. Okay, so let's look into the code for once. So as I said, I'm defining these two recursions. ME is nothing. ME is just the expectation of M, which is M plus 1 by 2. MSE is nothing but just the expectation of AI ka square. Okay, which I have said is nothing just M plus 1 into 2M plus 1 divided by 6. And starting with f of 2, uh, f of 2 is what? F of 2 is just a1 plus a2. So it is just going to be me plus me. P of 2 is what? Uh, P of 2 is P of 2 is a2 ka square plus a1 into a2. So a1 into a2 is nothing just like expectation, like those two terms are independent, so just their averages would get multiplied, which is me into me, and this is a2 square expectation, which is basically MSE. So this way I am calculating the initial values of f of I, and from I equals to 3 I will recursively calculate f and p, right? And then my final answer is what? F of n into n ki power n, sorry, m ki power n, and that is just my final answer. So the overall time complexity is just big O of n, and space complexity is also big O of n. So yeah, that's that for this explanation, like for this discussion. I hope you enjoyed the discussion. Thanks.